Chapter 5 now is thermochemistry, thermo meaning heat. Okay, when you're talking about energy, energy is the ability to do work or to transfer heat, and heat is one of the most common forms. But with thermodynamics, we're going to study that energy and its transformations, okay, how it transfers. And anytime you have a chemical reaction, you're going to have a change in energy. And in most cases, that's heat, okay? So we're going to talk about that. We're going to actually show you in the reaction how you can calculate it. So you can actually calculate how much energy will be released when you transform, elements into compounds or compounds into elements or whatever. Okay, so specifically, thermochemistry, its fancy definition, is the study of chemical reactions and the energy changes that involve heat. And again, anytime you have a chemical reaction, there's going to be a change in energy, and in most cases, that energy is heat. Now, it doesn't mean it has to get hotter, it can get colder. Okay, and we'll talk about that as well. So, thermochemistry, and the thermodynamics, I guess, if you want to call it. Thermochemistry is the study of chemical reactions and the change in heat. All right. Okay, so if you look here, I mean, there's graphs that show you them, but really the most important thing to remember about chemical energy is its potential energy. It's there waiting for you to use it. Okay, and there's an equation for it. We're not going to worry about that, but this is really the thing to remember when we're using. When we're talking about the energy, we're talking about joules. Okay, joules is the unit of energy, and again, I'll show you how to calculate that. It's actually kilograms meters squared over second squared, but we just need to know this, joules. Okay, so the unit of energy, of thermal energy, is going to be a joule. Okay, and again, that's heat lost or gained, basically. Okay, where it comes from is the attraction between the ions. Okay, we have this. Here's salt, and we have the attraction between the positive cations and the negative anions. Okay, when they're all together like this, they have energy. Okay, when you spread them apart, okay, now you have more attraction going on. They want to be back together again, but because you spread them apart, energy is released. Okay, so energy is released when chemical bonds are formed. Okay, basically, when you form a bond, they're more organized, so there's less energy there. And then when you break those bonds, that's when you get energy consumed. It takes energy to break the bonds. And when you form a bond, you get energy. Okay, so energy is released when a chemical bond's formed, because again, it's going from low potential to high potential energy. And then when a chemical bond is broken, that's when your energy is consumed. Okay, so again, there's 3 laws of thermodynamics. I think we'll cover 2 in this chapter, if I'm not mistaken. We're going to spend most of the time on the first law. The first law is energy can be converted from one form to another. You never create or destroy energy, you guys. And it seems like, well, I fill my car with gas and I have to fill my car with gas again and again and again. Well, you're changing the energy in that gasoline to mechanical energy. You're moving your car, and heat. So you're changing it to a different form. Okay, that's why you have to keep putting it back in. It'd be great if you only had to put it in once, wouldn't it? But you change it to a different form, and now it's not in a form that'll run your car. Okay, so that's why you have to keep putting gas in. But energy is not created or destroyed. Just like we talked about matter and mass, it's not created or destroyed. We just change it to different forms. Okay, when you heat your home, you use chemical energy. You either use propane or you use electricity. Okay, well, if this is true, that energy is not created nor destroyed, then you should only have to fill your propane tank once. But you burn that propane, you get the energy from it, you get the heat from it, and the heat doesn't totally stay in your house. It escapes. It escapes in the cracks in your windows, when you open up the doors and all that. So then you have to keep adding more. So you converted it to heat, but that heat doesn't stay. Some of it escapes, and that's why you have to do more. Okay? Sunlight is a chemical energy that's converted, but we can't do that. We count on green plants to do that. So plants absorb the sunlight and convert it to chemical energy in the form of glucose, food that we eat. Okay, so there's all kinds of examples of conversion of energy. And again, it's converting it from one form to another. It's not creating it, it's not destroying it. Okay? All right. When you're looking at thermodynamics, there's certain terms you have to understand. Okay? There's systems and their surroundings, okay? This piston is considered a system, all right? Energy can either enter or leave, and it usually leaves us heat, and then you've got work done because the piston goes up and down, and then your engine runs, and then you move, right? Matter cannot enter or leave the system. It's closed down here, okay? So this is the system is the hydrogen and oxygen in here, okay? The surroundings are going to be all this area out here and up here and all that, okay? So the portion of the universe that we single out to study is the system. In this case, our system is these guys, the hydrogen and the oxygen molecules, okay? Hydrogen and oxygen, all right? The surrounding is everything else. So these guys are our system, just these chemicals. And you'd think this whole area would be your system, but it's just the reaction that's occurring is your system. The surroundings are going to be here and up here and out here. I mean, it's all this area, especially here and here. Because really in a piston, what happens is these guys get ignited and then piston goes up. And then it falls back down again and ignited, and it goes, and that's why pistons do this, and that's why a car moves. Okay? Some of you guys that are mechanics know that, understand that mechanism much better than I do. But I know that we got little explosions and up and down and up and down, and when I press on the gas, my car moves. Yay! Okay. All right, so we have different types of systems, okay? We have open systems and closed systems. An open system is a region of the universe being studied that can exchange heat and mass with its surroundings, okay? This would be a closed system because you have, right here, you only have so much, okay? In a closed system, a region of the universe is being studied that can only exchange heat with its surrounding, okay? So an open system usually is a much larger system, and you have a lot more exchange going on than you do in a closed system. Okay, there's also isolated systems, and it's a region of the universe that cannot exchange heat or mass with its surroundings. Okay, an isolated system would be an area there is no heat exchange. There's nothing going on there. Okay, usually probably really extreme cold, like North Dakota coming up soon. I'm just kidding. Okay, so what happens in the internal energy? Okay, if you have a system, this is the energy, okay, and it's a positive number. That means what you started with, you end up with more energy than you ended with, okay, initial versus final. So when the delta E, the change in energy, is positive, what they call that is an endothermic reaction. The system absorbed energy from the surroundings, okay? So if your delta E, your change in energy, is positive, what they call it is an endothermic reaction. Okay, if it's negative, okay, if you have a change in internal energy, okay, so you end up with less energy than you started with, that means you had to release some to the environment. That would be considered an exothermic reaction, like burning something, okay? You lost energy from your logs to the environment, okay? So if there's changes in internal energy, okay, here's the vault is our system. Okay, we got our internal energy in here, okay? If our internal energy there you see gets bigger, in order to do that, it has to absorb energy from out here. Okay, so that's why the delta E, the energy, the internal energy, is a positive number. It gained. If the energy is lost out here, and again, usually it's heat, is lost to the environment, the surroundings, then your delta E, your change in energy, is going to be negative. So a negative number loses energy to the outside, a positive number gains energy. And again, this is gain in the system, gain in the surroundings, okay? So when energy is exchanged between them, it's either exchanged as either work or heat, and in most cases we look at it as heat, okay? To figure this out, the change in energy equals Q, which is the heat, and W, which is the work, okay? So we look at those, and again, if this number ends up being positive, then it's going to be what they call an endothermic. If this number is negative, it's exothermic. Okay. And again, if you look at Q, W, and E, okay, if it plus, it means it gained heat, negative, it lost heat. If the work done by the system, again, these guys are all going to be positive, these guys are going to be negative. And the big thing is the net. Okay. If it's positive, Again, it's called an endothermic. If it's negative, it's called an exothermic. And here you can see it. Okay, here's a reaction. We have some substance and we add another substance to it. Okay, and you can see when I took the temperature of this, it was 23 Celsius, sorry. Okay, I add this stuff to it and the temperature goes down. Ooh, negative 11. So it went down quite a bit. It went down what? 23, 34 degrees. So this became colder. So that must mean it had to absorb energy. And that's why it gets colder. The heat flows from the surrounding system and the temperature of the beaker actually drops. Here's the reaction that actually happened. This is hard to see, sorry. But we got barium hydroxide, which it's hydrated. And we add sodium cyanide to that. And it actually gets colder. So anytime the temperature goes down, what had happened for the temperature go down, because temperature is actually measuring the surrounding, not the system. So it's measuring the surrounding. And so because this got colder, well, where did the heat have to go? It had to go into the system down here. So that's why if it gets colder, it's considered an endothermic and it's a gain in energy. Okay. And here is an exothermic. This is a fun one. When you put potassium, potassium is a crazy reactive metal. Okay. You drop it in water and look what happens. It goes like fireworks. You can put a piece of potassium on an ice cube and the ice cube will burn. That's how reactive it is. But anyway, this is an exothermic reaction because if you measure the temperature of this, it's much hotter. So now the surrounding area is hotter. So the system must have given it that heat. So again, if your heat is released to the system, from the system into the surroundings, sorry, I said that wrong. If heat is released into the surroundings, then the process is exothermic. Okay, so endothermic, it's going to get cooler. Exothermic, it's going to get hotter. Okay, and I wish we could do a lab. I have some really cool labs where we do this, but unfortunately, you know how that goes. Sorry. Okay, so I think we're going to quit right there. All right, so we know endothermic and exothermic are two types of reactions, and they occur, you know, their type of reaction occurs if it gets colder. That means the system gained energy. It sucked energy out of its environment, the surroundings. And that's why it gets colder. And its delta E is going to be positive. Okay. If the surroundings get hotter, the temperature goes up, that means the system's giving up its heat, and that's an exothermic reaction. And a delta E is going to be negative. Okay. So that's what we got so far. And that's what we'll talk about when we talk about our thermodynamics.